the kind of setting that I want you to sort of have in mind here is a bunch of data that comes from devices, okay? So let's say connected devices data that are generated from mobile phones, from wearable devices, okay, any type of data like this. So essentially they belong to a user, and you have a bunch of users, they each have some data, okay? And collaboratively, those people want to get a service, okay? So maybe there's a service provider, and the users are interested in a service like, I want my device to recognize my voice. Okay, can you help me? You can think of many other examples. Essentially, okay, recommending some content based on the user activity log. Okay, let's say browsing web pages on your mobile phone or things like this. Some of the things that we're starting to see also is things like learning personalized treatments from wearable devices data. Okay, and so the kind of application you have in mind that has this personalized setting to it. Okay, so the thing that I want to learn might be a little bit, there might be a user-specific component to it, okay, like this personalized treatment, obviously. All right, so what is the kind of approach that, okay, exists out there to do machine learning in that kind of setting? The first sort of what I call extreme approach would be this one. I call it decentralized machine learning setting. So in this setting, essentially the service provider would ask all users to give their data, okay? So the devices would upload that data to some central database, okay, where we put all that user data. And then from there, okay, you may apply any kind of, okay, machine learning, data mining, data analysis type of things to build out of this data a model that then will be able to spit out predictions when you give it some new data, okay? So now if a user says something to the phone, okay, I'm expecting the model to be able to make some prediction, okay, about what is being said by that user, okay? So this is really the standard way of doing things, okay, probably the vastly dominant approach nowadays. So what you can say about this approach, that is good for utility in the sense that all this data is easily accessible by the service provider, by the machine learning algorithm, for instance. So because it's in a centralized database, I assume I can efficiently access it, I can efficiently process it, maybe by distributed computing resources and so on, okay? So that's good. I have sort of easy and unrestricted access to the data, okay? What can be not so good, first in the perspective of the user, is the lack of user control, okay, over the data. In this model, essentially the data is being collected. In many scenarios, it's sometimes not quite clear what is actually collected, okay? When you're browsing the web, for instance, there's a lot of tracking that's going on, okay? And it's not clear what is collected, who can really access it, what it is used for, okay? So in this respect, it's not that great for the point of view of the users being able to control their data. It's also just from its very centralized kind of architecture is really vulnerable to attacks, okay? So you have just one very big database here, okay, that maybe someone can try to attack and get the data that's inside it, okay? So you might have heard about the Yahoo data breach, the Yahoo data breaches, I think, because that happened, I think, several times. I think a recent one, probably 2014 or something like this, like they got the personal data of 3 billion users essentially stolen, okay? And essentially what makes that possible is really this architecture, right, where all the data goes to one place. There are also more subtle things like subpoenas, where the company that holds this database can be commanded by, let's say, the government to give data about particular people. That has happened in like Twitter WikiLeaks court order thing, where the US government asked to Twitter essentially to release all the information that they had about Julian Assange and people like this, okay? And Twitter was not even allowed to actually let those people know, okay, that their data was being requested. So, okay, those things are possible because of this sort of centralized setting. This was more on the user point of view, let's say, but also there's a downside maybe on the side of the service provider, which is this costly infrastructure that needs to be maintained, okay? You need to be able to store all this data, you need to be able to secure it so that it's not easy to attack it. Okay, you need to do computation over this data, so potentially involving a lot of machines and so on, okay? So before I jump into the kind of architecture that we're gonna be interested in this talk, there's a second extreme approach, okay, which is purely local learning. This is very simple, okay. I just leave the data on the device of each user, and then they just learn on their own. They don't share anything with anyone, okay. You could say it's good for privacy and for data control from the user in the sense that no information is ever exchanged, okay. You keep your data locally, you process it locally, that's it. So in a way, it's best in that respect. But of course, on the other hand, it's really bad for utility because you don't get to do any kind of sharing of data, okay, putting in common some relevant information across users, okay? And so if you have users that have not much data, maybe they joined recently the service or something like that, they're not so active, then clearly this is not going to work out very well for them, right? Okay, so what I'm going to sort of be interested in today is what I call the fully decentralized learning approach, okay, where I'm still going to, like in these purely local models, I'm going to keep the data on each user device, okay? The data is never going to leave the devices, but I'm going to allow some communications between users, okay? And the way I'm going to allow communications is really in a sort of peer-to-peer and asynchronous manner. So you can see that this architecture has a graph where a node is a user with its database, and there's a link between two users if they can exchange information directly, okay? In this way, so this buys us like two things, okay? At least the first thing is there's no single point of failure or entry anymore, okay? As in, okay, when you have like a more distributed server client type of architecture, okay, there's still the server that can be a single point of failure or entry. Here, it's really fully distributed. And it provides scalability by design. We'll see the kind of algorithms that we have in mind are really going to rely on local updates in this network graph. And in an asynchronous fashion, in this way, the graph can be very, very big. The users don't need to know what's going on very far in the graph. Okay, they only need to compute locally and exchange information with their immediate neighbors. Okay. So there's a recent paper who shows like, okay, that those more master-slave kind of setting can put a really big communication bottleneck also on the master node, for instance, the server, which here sort of disappears. Okay. Feel free to interrupt me, by the way, at any time. Yeah.
So when you say no single point of failure, you mean that to obtain all the data, you have to corrupt everyone, or that to obtain one person's data, you have to corrupt more than that single person?
No, I mean, more likely the former. So I can potentially still hack some individual user, but then it doesn't turn into like a really mass leak, like in the Yahoo type of thing that I was mentioning. Okay, it's an interesting, also question of maybe going a little bit further and even allowing that attacking a single user will not lead to any leak at all. In this case, I'm still going to assume, okay, yeah. So what I mean here is if I want to get most of the data or a lot of data about the users, then I will need to be able to attack separately like a lot of people, okay, which seems a little less likely, okay? All right, of course, so those were some advantages that you can think of about working in this setting. Of course, there are challenges associated to this approach. The first one is how you can efficiently learn in such a setting under those communication constraints, so in particular maintaining this locality of updates that make the algorithm efficient. The second one is, of course, how to prevent users in the network from inferring data, sensitive information about others in the network, okay? I'm never going to share the data directly, but I'm typically going to share some information computed from the data, and so maybe I don't trust the other users in the network, so I need to be able to make sure that they don't learn much about me, okay? Okay, there's also another interesting question, which is trying to prevent users from manipulating the outcome of the algorithm. I'm also interested in that problem, but I'm actually not going to talk about this one today. So mostly it's going to be efficient algorithms and then dealing with privacy. So those things, I'm going to make those things more formal, of course, next. Okay, so before I delve more into the approach, to answer the first problem, we need, to be able to make algorithms that are efficient in this fully decentralized setting. And so one type of algorithm that typically is efficient is what we call gossip algorithms. Okay, so this is going to be some principle that we're going to try to follow so that we make sure our algorithm can scale to a very large number of nodes in the network. So So those algorithms works as follows, okay? So essentially you see each user as some kind of independent device that can wake up asynchronously and in parallel, okay, according to some local clock, for instance. Each time it ticks, a particular user is going to wake up, and when the user wakes up, what it does is essentially select a random neighbor and exchange some information with that neighbor, and then does that over and over again, okay? So equivalently, you can see this as with a global iteration, where at each of those global iterations, there's a random edge that gets activated, okay, which corresponds to a user waking up and contacting a neighbor. So I'm going to illustrate this on a very simple problem, which is averaging, okay? So decentralized averaging. Imagine in the network, the data is just one value, okay? It's a real number. And what the users want to do is just compute the average in that network, okay? So there's a really simple gossip algorithm to do this. It goes like this, okay? At each iteration, some user wakes up, contacts a neighbor. And what they do in this averaging problem, they just average locally their value, okay? So they got 4 and 6, now they got 5, okay? And essentially you just go like this, okay? And you can show that if you do this long enough, essentially you converge to that state where everybody got the average. And you can derive like how fast this happens, and in particular, there's some connections here with spectral quantities of the network graph, which essentially give how fast information sort of propagates in graphs. So intuitively, the more connected the graph, the faster this is going to converge. Okay, but the main point here is that this is essentially simple and asynchronous. It's purely local, okay? So I never have to wait for other people at the other end of the graph to do anything. People compute on their own, contact neighbors, exchange, and so on, okay? So it typically is very well suited to large networks, okay? So we're going to aim for algorithms that are essentially in this kind of fashion, okay? Yeah?
Which information exchange between which information will be exchanged between the users? The raw data or anything else?
No, okay. So, of course, I'll make that clear soon, okay, when I define the algorithm. The short answer is never going to be, in the case of the algorithms that I'm going to present, never going to be the data itself. It's going to be some quantities computed from the data. Okay, and then we'll see how we can make sure that those do not reveal too much information about the data itself. Okay, but yeah. So here, okay, in a way, in this example, averaging example, I really communicate my data. It's not going to be the case in the algorithms that I'm going to introduce. All right, so this was only for averaging, okay. Maybe not so interesting problem. Maybe it is, actually, because you can do a lot with averaging. But okay, what if you try to do something a little bit more advanced, like optimizing some loss function over data, okay? So machine learning in many settings, it can be essentially written as optimizing, finding the parameters of some class of models that minimize, let's say, some average loss over the data, okay? That predict best the data that you have, okay? And so there exist essentially gossip algorithms to do this, okay? Where the goal is to find the model that performs best, essentially, on the union of the data for the users, okay? And those approaches go like this, okay? I'm just giving here, again, like a general idea. At each step, the way those things work is, okay, this is gossip algorithm, so I got some random edge activated. Assume everybody starts with the same sort of, okay, initial model. Then, okay, when the iteration starts, okay, two users contact each other. They do perform a local model update. Okay, so basically they look at their local data and they update the model they currently have based on their data. And then they do some kind of averaging. Okay, so here we cover sort of similar ideas as before, except that we sort of alternate between making things better on the local data and averaging so that we can reach a consensus at the end, okay? So there's several invariants. You can average the parameters, you can average the gradient when those procedures are based on gradient descent. Okay, there's various ways of doing this, but again, I'm not gonna go into the details here of those algorithms. This is just to give you sort of a high level idea, okay, and when you continue, essentially you converge to something like this. Again, everybody has the same model, which is the one that minimizes the loss function that you wanted. Okay? And so this brings me to finally to what I'm going to focus on today, which is going to be a variation of this problem, which is the more personalized case, okay, where what I'm trying to do is not converge to a model which is the same for everyone, a single global model, but I want to have models that are personalized for each users, and yet, of course, benefit from information from other users in the network, okay? And so the general idea of the methods are going to be to trade off the accuracy of the model locally for the data of that user with some kind of smoothness property on the models, which is going to mean essentially similar users out there in the system that are looking after a similar thing. I should try to, okay, get inspiration from them and have a model that is like the one that they have. Okay, so we're going to have something. Okay, we're going to make sort of an assumption on the graph of user that it characterizes some notion of similarity among the tasks. Okay, among the users. All right. Any question at this point? So again, this was my high-level introduction. So any details about this particular thing, this is what I'm going to essentially talk about now. But if you have some questions about the general setting.
So I'm wondering, is there an equivalent of a centralized thing for this type of learning?
There is, yeah, there is. So
what is is this multitask learning? Or
yeah, exactly. This is the kind of formulation that we're gonna build on. So this problem, just like the consensus one, we're gonna formalize as solving an optimization problem, which is different globally, but then that you solve in a decentralized setting, and it's gonna be very similar to things in in multitask learning. The main difference is that we're gonna, okay, here it's more like an extreme multitask learning in the sense that most of the time this is gonna be interesting where there are a lot of users, so a lot of tasks, who typically have not so much data, okay? And many multitask learning sort of problems have focused on more the, let's say, few tasks with more data. So here we want to scale to 1,000, okay, maybe millions, even like tasks, okay, because each user is a task. Yeah.
Are you losing the randomness when you start attaching, creating links with similar users?
So even in the simple averaging case, so maybe I can repeat the question. So the question was, do I lose randomness?
Yes, sir.
No, I was just wondering if you're losing the randomness when you're using similar users to create your network.
Okay, so the randomness that I had in the algorithms that I showed before was really in the way users wake up and select neighbors in the graph. Was always assuming that the network graph was given in the first place. Okay, so this graph you can think of generating in many ways, but I'm going to assume it's fixed, and the assumption I'm going to make in this work is that it's fixed and it conveys some notion of similarity between users. Yeah, but there's still going to be randomness in the algorithm itself, which is waking up and contacting random neighbors. Right? Cool, so now I'm gonna start going a little bit into the details. So what I'm gonna do is essentially not assume first any privacy constraint. What we're gonna do is never communicate the data itself, but I'm not gonna have some explicit privacy constraints in the first place. And then I'll show how we can modify the algorithms to make them, in our case, differentially private. Okay. All right, so a little bit of notations. Okay, so we work in the supervised learning setting. So essentially, the problems here are going to be about predicting some label y from some observation x. Okay. The set of possible prediction models that I'm going to be working with, I'm assuming they're indexed by some parameter theta, which is in p dimensions. Okay, so essentially I want to learn theta. I'm going to also assume that essentially how I measure the error of a model on a labeled observation, this is given by this L. Okay, it takes a model an observation and its label, and it gives me some notion of error, okay? And this is what I'm going to optimize, okay? And I'm going to make the assumption that this thing is a convex function in theta, okay? We're going to have a set of learning agents, okay, 1 to n, and each agent is going to have some data set, Si, so it's a bunch of labeled points, okay, which, okay, you can see, I'm not going to use this assumption explicitly, actually, but you can think of those as being drawn from the user distribution, okay, because we assume each user has its own problem, so essentially, okay, the difference in the problems are going to come from the kind of distributions that the data is drawn, okay, so this mu I is, okay, the distribution of the data for user I, okay, and importantly, we're going to have data sets that might be very unbalanced between users, and this is what really we're going to rely on this in a way. So the size of the data set of agent I is mi, okay, this thing can be, okay, small or large depending on the user, okay, so some users might be very active, or they signed up a very long time ago, they have generated a lot of data. Some users might just have joined the service, they have almost no data, okay. Okay, so this is more just, okay, recalling the high-level goal of machine learning, okay, from the perspective of agent I, what agent I would like to do is learn a model theta I, which has small expected loss, okay. So this is the expectation of the loss over data drawn from the distribution of user I. Typically, we don't know, of course, this distribution, so what we do in machine learning, okay, or at least a standard approach to address this problem in machine learning is things like regularized empirical risk minimization. So if I assume agent I doesn't talk to anyone, okay, is not aware that there are other users out there, what agent I could do is learn what I call a solitary model, okay, which is just essentially finding the parameter theta that minimizes the average loss over its local data set, plus maybe some regularization, okay? You can argue this is, okay, what agent I would do if it was on its own, okay? And now my goal is going to be to improve upon this, obviously, because if I cannot improve upon this, then, okay, users might just, okay, stay on their own. There's no incentive in collaborating, okay? So this is going to be my baseline, essentially. So to allow doing better than the baseline, I need to, okay, make some assumptions so that collaboration makes sense, okay? And again, like I hinted at earlier, this is going to be through the network, okay? So the network, I'm going to see it as some kind of weighted connected graph, G, okay, where the edges are weighted by this matrix W. I'm going to assume it's symmetric, non-negative. The weight is 0 if the edge doesn't exist, and otherwise, this Wij is going to be essentially indicate how similar the two users are in terms of objective, okay? And for the purpose of this talk, I'm actually going to assume this is given to me by some oracle that tells me, okay, those are the users that, okay, are after similar goals. In practice, there's, okay, it depends on the application. There's many ways you can generate this. Maybe you have some side information on the users, like a profile or something like this, which is different from the data. In some applications, there's obvious way of generating this. In some cases, you can also try to learn them from the data or estimate them from the data. I'm not really going to address this part, okay? So feel free to, okay, come back at this issue at the end. I can give some more details on how to get those, but I'm going to assume they're given. So this is going to look like this, essentially the setting, okay? So graph, each user has some data set, okay? Some people have bigger data set than others, and they have weights, okay? When there's a link, there's also a weight that indicates how similar those two users are, okay? And importantly, I'm going to assume that the agents only have a local view of the network, so they only know their neighbors and the weights that are associated to it. They don't need to know anything else. Okay, so now how can we try to learn in this setting? Okay, now that we defined it a little bit more formally. I'm going to present sort of two ways of framing the problem. The first one, this model propagation one, is going to be more maybe some kind of warm-up approach, okay, which is good. And the idea is going to be the following at a high level, is each user is going to look at its data and come up with some model that looks the best locally. And then I'm going to do some kind of smoothing over the network graph to try to aggregate some additional information from neighbors, okay? Trying to make the model sort of smooth over the graph. Okay, so how do we define this? So first I'm going to define like a global objective function. Oops, okay, oops, okay. So I'll just use this notation CI to denote some what I call confidence. Okay, this is sort of informal in the model that the user I has in its model. Okay, so you can see this as sort of being proportional to the number of training points. The idea here is that we need to keep this into account when we merge models with neighbors. Like if I had a lot of data, then probably I'm more willing to stick to what I learned on my own than getting information from others. So this is to sort of deal with this imbalancedness, okay, imbalance essentially in the training data. And what I'm going to try to do here is try to optimize this objective function. So this objective function has two terms, okay. I'm trying to learn a set of model big theta, okay, so it's n times p, model for each user, n, and in p dimensions. And I'm going to trade off between two terms. So the blue one is essentially requiring that my new model theta I stays close to the original model that I learned on my own. And this is weighted by this confidence, okay? So the more data I had, the less I am happy about the idea of diverging from this. And the other term is the smoothing term, okay? So it's essentially saying if wij is big, so if the similarity between two users is large, then I want the two models parameter to be similar in two norm, okay? So here for people who know or familiar with semi-supervised learning on graph and things like this, this is essentially similar to those label propagation type of approaches, at least for the objective function. Okay, and this gives me sort of my goal, okay? Of course, there's a closed form solution for this problem because it's quadratic and convex in theta, but I cannot compute this without sharing everything about the network, essentially. The models that I learn locally, the weights, and so on. And so this is precisely what I'm trying to avoid. So I need to come up with some kind of gossip-like algorithms to find the solution of this problem. Okay, so we're going to use an asynchronous gossip algorithm. Okay. So this is just a reminder of what I said a bit before. So each agent has some random clock. So you can see that's some sort of like a Poisson clock. Okay, it's distributed as a Poisson. And wakes up when it ticks. And so we're going to assume that there's a global counter T that ticks when one of the local clock ticks. Of course, I'm not going to assume this is known by the agent because that violates this sort of fully decentralized setting that I mentioned. This is just to spell the algorithm in a nicer way, okay? But essentially, this T is going to be unknown to the agents. They're not going to need it to run the algorithm. And what we're going to do essentially is maintain some outdated knowledge about neighbors, okay? So the algorithm is going to assume that each agent is going to keep locally in memory its own model and its last knowledge of each of these neighbors' model, okay? Which is going to be potentially outdated. And the algorithm looks like this, okay? It's going to be actually very simple and also very simple to interpret. So imagine at step T, some agent wakes up, okay? Imagine it's I, okay? Then I does two actions. First, a communication step, so this is gossip. So I is going to select a random neighbor J, and they're going to essentially update their knowledge of each other, okay? So they're going to exchange their model and say, oh, okay, this is my current model. Please store it. And okay, they're both going to do this, okay? And then they do an update step. So the two agents then update their own model based on the current knowledge they have about their neighbors. And so essentially, this is the update that's over here. And you can see that it's essentially a convex combination between doing a convex combination of the neighbor's model, okay? So this is this term here. So the bigger the weight, the more weight I give to that neighbor model. And the other term is essentially my initial model. So this is really, okay, we see here really this trade-off, right, between trying to stick to the original thing that we had and trying to get information from neighbors. Okay. So what can we prove about such an algorithm? Actually, for this algorithm, we have sort of like convergence in expectation. Okay, so what this theorem is saying is that if you run the algorithm long enough, so when t goes to infinity, the expected models, okay, at each node converge to the true ones, okay? or what I mean by the true ones is the one that minimize the objective function that I defined earlier. Okay. So I don't really have like a rate of convergence here. I only know it converges asymptotically, essentially. And okay, the kind of way this can be proved is essentially by seeing the algorithm as some kind of random iterative process, okay, linear sort of dynamic system, where my parameters at time t plus 1, they're essentially derived from the parameters at time t. And the way they're derived is a transition matrix, which is random, a of t, which is applied to this parameter, and then there's also a b vector that is added, okay, and this, both a and b are random, okay. And then essentially what you need to do to show that this thing converges is to study the spectral radius of the expectation of that transition matrix a of t. Okay, and essentially if you can show that the spectral radius of this expected matrix is smaller than 1, then you get that it converges, and you can analyze that it indeed converges to the right quantity. Okay. So this is essentially how this is analyzed. Okay, so there's a little bit of rewriting the algorithm here as some kind of just linear update. All right. So now what if I try to do something a little bit more clever? So what I did so far here was just, okay, look at my data, find some model locally, and then forget my data and just try to, okay, aggregate and essentially merge my model parameters with those of my neighbors, okay? So in a way, I just forget the data, okay? So imagine even if you do linear classification, if it's in high dimension and you don't have so many points, if you just look at your data, there's like many different set of parameters that can be as good on your local data, and yet using the previous algorithm, you sort of commit to those and try to not get away from those initial parameters, okay? So something more interesting, okay, more powerful that we might want to do is something like learning and propagating models at the same time. And this is going to be done by changing the objective function a little bit, just changing the blue term, essentially replacing trying to stay close to the initial model by just the local loss, okay? So this Li of theta here is just the average of the loss function on the local data set of the agent I, okay? So now I'm trying off keeping good accuracy locally and having model parameters that are similar to those of my neighbors. Notice that I can recover like two extreme cases here. So if I have mu that tends to infinity, I actually recover the case of just learning independent models, like purely local models. And if I have mu tending to 0, then I recover this consensus learning problem that I talked about in the introduction, which is essentially learning a single global model that performs the best on average over the users, okay? Yeah.
It seems to me that when mu goes to 0, you're forgetting your data again.
Okay, so when you take it equals 0, yes. If you get it smaller and smaller, okay, then essentially this becomes like a hard constraint.
Mm-hmm.
So you're forcing each theta I, theta j to be exactly equal.
Okay.
And yet you still have some non-zero weight on this side, and so you can really see this even numerically reducing mu, and you essentially still allow the models to be different, but they really converge to just being the same or having negligible differences. Yeah. I'm not saying this is an interesting case in practice. I mean, if you're interested in just a single global model, you probably just should not go with this approach, right? But you can still recover it from this general form. All right. Okay, so now I want an algorithm for this slightly more complicated problem now, right? Because essentially at each iteration, I'm going to look at my data again and make updates. So we have gossip algorithm for this problem. For simplicity here in this talk, I'm going to consider like a slightly different communication model, which is going to be the broadcast communication model. So now when agents wake up, they send message to all its neighbors directly. And the neighbors are not expected to send any reply. They're just storing what was sent by that user, okay? So previously I was selecting a single user and expecting a reply. Now I'm just sending to all my neighborhoods. Which one is more efficient really depends on the kind of network you're dealing with. If you have like wireless communication, for instance, this is very natural because wireless is inherently broadcast, right? When I send something wireless, everybody close enough essentially can hear it. Okay, so this is more, I'm going to be able to spell this version of the algorithm more nicely in this setting, but we also have like a gossip version for it. Okay, so now the algorithm is going to be mixed more with some convex analysis, okay, some convex optimization stuff. Before I was just more or less doing some kind of weighted averaging, okay, over the network. Now I need to do this propagation and at the same time optimize locally my loss function, okay. So now we need some assumptions essentially on the kind of properties that the functions have, okay. So those are quite essentially technical assumptions so that you can derive rates of convergence for the algorithm. And they're very standard, okay, so we assume that the local loss function of each node is Lipschitz. Its gradient is Lipschitz, okay. In fact, we're going to look at blocks, okay, so if you derive with respect to the model of user I, then you can compute like a block Lipschitz, okay, constant. So I'm going to assume this is bounded. Actually, I can compute it. And I'm going to assume, later actually, I'm going to assume strong convexity. You don't really need to assume that, but okay. It gives you faster convergence. So when you use like a L2 regularizer on the local loss, typically you get like strong convexity. So these intuitively just sort of bounding upper and under bounding the curvature of the loss function, okay? So those are really standard quantity. And okay, so now what is the algorithm going to look like? Again, it's going to actually be quite simple, at least to understand, okay? So assume now that, again, agent I wakes up at step T. I'm still going to do 2 steps, okay? First step is agent I is going to update its model. And basically, it's going to update this model in this way. It looks very similar to before. We still do convex combination of the parameters of the neighbors. But now the other term is essentially a gradient step in the loss, okay? So negative, I'm going in the direction of the negative gradient of the loss, so I'm trying to reduce the local loss, okay? So it's quite intuitive. So now I'm trading off between those 2 things, okay? And again, the importance that I give to both terms really depends on still this confidence CI, so essentially how much data I have, okay? If I have a lot of data, I'm going to actually trust my own gradient of my data a lot more and not put so much weight on the neighbors. Okay, and once you have done this, essentially the agent just sends its updated model to the neighborhoods, okay? So it does a broadcast step and send to the neighbors so that they're up to date with the new set of parameters for agent I. All right. So the convergence of this algorithm actually is quite easy to analyze because you can sort of reduce it to some sort of block coordinate descent algorithm. So I'm not going to sort of go into the details here, but essentially this result, okay, is sort of comes from free once you realize the algorithm I just shown is some sort of coordinate descent applied to the objective function that I defined. And so the kind of here we get like a much stronger result than what we had before. Okay, we get like a rate of convergence. Okay, so the expected gap essentially between the best value of the objective function and the one I get after a big T iteration, this goes to 0, and essentially this is geometric rate. Okay, so here I have something strictly smaller than 1 to the power T. So essentially I'm cutting the gap to optimality. The initial gap that I have, I'm cutting this by a constant factor at each iteration. Okay, so those are sort of like the fastest type of convergence that you get in convex optimization. This is due to strong convexity assumption. Okay, if you don't assume strongly convex, you just assume regular convex, you get something in 1 over T. Okay, so again, I'm not going to the details here of the analysis because essentially we managed to come back to some existing approach for actually centralized optimization. Okay, So this algorithm is though very simple, is it's going to serve as basis to make algorithm differentially private. So if you don't have question at this time of this particular algorithm, I'm going to then go to essentially the sort of privacy preserving setting.
So this has nothing to do with the graph, right? So this is a property of the centralized graph. So this theorem doesn't speak about the distributed version.
It does. So it really gives the convergence speed of the algorithm, the decentralized algorithm. There is some dependency on the graph, essentially in those parameters, and like in the sigma and this, essentially the strong convexity and the Lipschitz constant. There are quantities in there related to the graph itself, like the degree of nodes and things like this. So the dependency on the graph is not as precise as some other algorithm, like in the averaging case, you get something that's quite nice. Depends on the spectral quantity, essentially algebraic connectivity on the graph. We don't really recover things that are so precisely tied to the graph topology, but we still get here some dependency, essentially. So you can identify some bottlenecks, like, oh, if some user is completely isolated from others, like has a degree much smaller than the average. You can see in those things that this is going to slow the convergence.
Okay. Can you translate this type of optimization guarantee to something about the excess risk at the user's level?
Not really. So the kind of thing that you can do is sort of combine this with some bounds that are known for multitask learning. But actually, this is a really interesting question. I think those bounds are not so satisfying, at least the work that I know, because they just quantify the sample complexity. So they're saying if I am doing multitask, so I also, I have some, when I have some regularizer like this, essentially I can learn faster because I'm also getting information from other tasks. But it doesn't say anything about, essentially it's just the sample complexity, so it says the best, how fast it converges to the best thing that satisfies this. Okay, so it doesn't really tell you whether your similarity is appropriate or anything like that. In a way, it's completely independent from the way you computed the similarity between tasks. So a very interesting question, I think, is to make clear the link between, let's say, divergences on the distributions of the users and, the kind of generalization guarantee that you can have. So this is something that I really want to investigate. So far you can get bounds, but that will not make this interest of having chosen particular similarity weights clear. Okay, it's just going to tell you, essentially, the stronger this term, the best I am in terms of sample complexity, but it doesn't tell you if the model you run is good or not in generalization. I hope it's clear.
As the users are training the n-class classifier, yes, all of them.
I'm sorry, can you repeat?
All of the users are training an n-class classifier, yes?
Sure. So
So is there any constraint on the data of each user? For example, each user should have data of several classes or no?
Yeah, so that's a really interesting question. So here I don't make any assumptions, okay? So I'm just optimizing parameters, and so those parameters could be, I don't know, something like multinomial logistic regression, okay? So you can deal with multi-class. Then you have to adapt a little bit, probably things like how you average the parameters, okay? So you probably need to average per class, and then have weights, also confidence weight that depend on how many examples of a particular class the agent have. Okay, so we haven't really explored that much, so the experiments I'm going to show up binary classification. But yeah, surely there's going to be some dependency, so not so much on the algorithm. So the algorithm you can run irrespective of the label proportions. You still have this guarantee that holds. Whether the models are good, obviously in generalization, obviously will also depend on this. Okay, see, if I had no example of a particular class, okay, I need to make sure I'm not, I'm averaging properly with other people so that, so there's a few adaptations at least that you need to do practically to to address imbalance in the class distribution. Yeah. All right, any other question before I jump into the privacy preserving bit? Okay. So, okay, you might have noticed, like in the algorithm that I presented, essentially I never shared the data directly. Okay, so what I did is sharing model parameters, essentially in all the algorithms. So okay, some people sometimes can argue, oh, it's good, I don't share the data. So, okay, so as far as companies goes, I've seen this kind of talk a lot. Like I think nowadays, like in a lot of contexts, people are already happy with this sort of notion of privacy, although it can be pretty bad. It's saying, okay, I don't transmit the data, so it's fine. Of course, it's not that simple because we compute a sequence essentially of parameters computed from data. And so there's cases where you can show that you can recover some information about the data of users. Okay, so there's work on like those model inversion attacks and so on. And when things are linear, it's even worse because you essentially get to observe gradients. Okay, so there's a lot that you can essentially recover from what we exchange. It's not the data itself, but it tells a lot about the data. So we'd like to avoid this, okay, make sure this cannot happen, that doesn't reveal too much information. So first we need to define sort of the adversary, okay, so what kind of person are we trying to protect from? What we're going to try to protect from here is, okay, you can see it as the NSA, okay, more or less. Essentially, this adversary is going to observe anything that gets transmitted on the network. Okay, so anytime a message is sent between users, this adversary is going to take it, store it somewhere, okay, and at the end of the algorithm is going to stare at it very deeply, and try to essentially infer as much as possible about the data. Okay. Of course, I'm going to assume the internal memory of agents is safe, at least for the purpose of this, because okay, otherwise there's nothing I can do. Okay, if the adversary can just read my data, then okay. So notice, of course, that in this against this adversary, this purely local models, okay, learning in isolation, of course, is perfectly private because I don't share any information with the outside, so the adversary doesn't learn anything. In our case, we're going to still share some information. And so the question is, okay, how can I trade off, okay, between sharing meaningful information and not revealing too much about my data? So we're going to try to guarantee that no, or more realistically, little information is going to be leaked by the algorithm about the local data set. So for this, we're going to rely on differential privacy. I think there has been recently a very detailed tutorial about differential privacy that some of you might have attended. I'm going to sort of not go too much into the details here, but of course, okay, recalling the definition and making a few comments about it. So, okay, differential privacy is essentially if you consider some algorithm M, okay, which is randomized, okay, so it takes an algorithm as input and with some probability spits some output, okay, and essentially we say that this algorithm is epsilon delta differentially private is for all pairs of data sets S prime which essentially differ in a single data point. So here it's one data point gets replaced by another one, okay? Otherwise they are exactly the same. Then for any possible output that the algorithm can return, essentially the probability of seeing one output if I apply the mechanism to S or to S prime essentially doesn't change too much, okay? And doesn't change too much is expressed in this way, okay? So epsilon in particular tells you how much difference there can be in this probability of the output. This needs to hold for any output, and then you have a delta here which gives you a little bit of slack against like very unlikely events, for instance, okay? So what this guarantees essentially is the output of M is almost the same regardless of whether a particular data point was used in the algorithm. This is really what this is saying, okay? And so this definition is information theoretic, so there's no computational assumption like in some more, okay, crypto type of approaches which rely on an adversary not having too much computational power so that it cannot break the encryption or things like this. Okay, here there's no computational assumption is really, okay, about the information that's contained in the outputs. Okay. So we know many simple ways of many essentially mechanisms to make an algorithm which is not private, okay? And here, as far as the way we ensure the differential privacy, there's really no particular thing clever here. We do the usual thing, so you look at the model updates and you see how sensible that is to a single data point in the data set. And once you have that, you know how much noise you need to add essentially to this quantity to make sure that differential privacy is satisfied. Okay, so we don't do anything very clever here, we just apply existing stuff. So the updates now becomes like this, okay, so this was just the update that I used before for the broadcast algorithm. The only change is I add this eta I of t, okay, where eta I is drawn from a Laplace distribution with some scale, okay, so variance si of t. Okay, so I'm going to allow those scales to be different depending on the iteration for full generality. Okay, and then this gives sort of like a noisy iterate, and this is the thing that I broadcast to my neighbors. Okay, so this is really the same algorithm as before, except for this noise addition. Okay, so this is the privacy guarantee that you get, so I'm going to also be sort of short on this because this is just an application of existing result. Essentially, if you assume that agent I wakes up at a particular set of iteration, and he used a noise which is sort of inversely proportional to some epsilon I and the size of its data set, then essentially the sequence of all the model updates that it shares satisfies epsilon I bar differential privacy, where this epsilon I bar is the sum of the epsilon i's that I used at each iteration. Okay, so this is this composition property of differential privacy, and you can actually do better than just the sum. Okay, there exists some stronger composition theorems. I'm not going to go into these. Okay, so the idea is here at each iteration, you let each user use some user-specific privacy parameter, epsilon I, and then the users sort of allocate their privacy budget across the number of iterations that they wake up, so that overall, okay, they get the budget that they wanted. Okay. Yeah.
I was going to ask Adria's favorite questions. He's not asking. Okay. So the MI there means that this differential privacy guarantee for a user protects like an individual record, an individual data point of this user, as opposed to the whole data set.
That's true. That's true. Yeah, yeah, yeah.
So my new favorite question. So the hyperparameters are known to the adversary, like similarity.
Yeah, yeah, yeah. The adversary knows, yeah, everything there.
Mu and CIs and all that.
Yeah, yeah. So here you can really see, okay, I didn't frame it this way, but then the differential privacy setting we assume here is sort of quite close to local differential privacy, because really I want to be private with respect to the outside of myself, right? Anything that I show to the outside world, I'm assuming, okay, this has to be differentially private. So I cannot rely on some trusted aggregator or anything like this to do some aggregation.
Yeah. So related to that question then, if I have differential privacy with respect to my data set, but I'm very similar to Borja maybe, and you then in this setup you would have access to all his data set and all my data set except for one entry as an adversary, right?
Sure, sure.
Knowing that someone is similar is bad because intuitively, so you still have differential privacy guarantees, but
Yeah, yeah. So
it's weaker than the other notion that where you get it. I don't know how to interpret this. Yeah.
yeah. So okay. So it's. I think this doesn't challenge differential privacy itself. Okay. I think what you're saying is. This is also boils down a little bit to our discussion earlier. Is to say, okay, then there might be some correlations then between the data of users, because I know they're similar. Maybe I could exploit them. And okay. So.
But it's
Yes, but
is fair in the sense that no differential privacy will not give you privacy if you do exactly what your neighbor does and your neighbor like
That's-
sells
yeah,
or
Yeah.
there's any problem with the differential
but that I think that's true.
maybe you could even exploit this to get more privacy out of epsilon.
Yeah, that's a good point.
So your adversary can sniff all the network, so it can, you say that they can have the sequence of all the updates.
Mm-hmm.
So differential privacy is about, as I know as a classic, if I'm, if my data is used for learning this model or not. But here, when adversary sniff everything, can know in which time, which user data is used to train the model. And
Okay, I think I see what you mean. So here, probably the short answer to your question is that what I consider as output of my mechanism is the entire sequence of updates that is shared by the agent during the execution. Okay, and this is over this that I want to prove differential privacy. So my output is not just one parameter update, it's really the whole sequence. Okay, so I put this in a set and this is my output, and I want that this jointly, all those parameter updates that I shared, they satisfy differential privacy. And so this is where, okay, you can change a sample in the user data set or not, and see how that impacts this output.
so it's about the privacy of the privacy of some part of my data, than the privacy. You know, I mean, for example, I have some personal data, and this data, after adding noise, this data is used to learn a model.
Mm-hmm.
Then I share the parameters. But at that point that I share this parameter, adversary know that this update is because of mine. You know,
He's making that update differentially private.
yeah, I mean,
Yeah, I'm not really sure I understand your point. But yeah, essentially what the adversary observes about the user is the entire, you run the algorithm, okay, and sometimes that user wakes up and so it sends some parameter to the outside. The adversary records this, okay, and then it has this whole set of parameters that was shared by the user, which in each time this update was computed by looking at the data set, okay, because we do gradient. And I want this entire thing to be DP. Okay. We can chat a little bit more later if we can try to clarify. Yeah. There's two.
So if you keep running it, your epsilon set based on the number of iterations. So if you kept iterating, you'd have no, or your full privacy guarantee would be degraded, right?
Yeah, exactly. So, okay, I'm going to come to utility just next, but essentially, yes, I'm going to have bounded a number of iterations. Otherwise, because I have to split my budget across the iterations, okay, then it degrades. One thing is good is that I do this user-wise, okay? So if you think about now, if I have more users in my network, essentially what I can do is I can still grow the number of global iterations by the same linear factor. So that is kind of nice in the sense that if I add users, I can still do more iterations globally, okay? Maintaining the same number of iterations per user, but I can still. So this allows me to scale to large networks.
So depending on whether you're glass full or glass empty, you can say you'd either terminate iteration for a given agent once the budget is depleted.
Yeah.
Then the model you've got that's what you got.
Yeah. So okay, in practice here, what we would do is just agree on a number of iteration per user, and okay, once a user is done with his number of iterations, it just stops updating. Yeah.
I have a kind of related question. So, do you have like a recipe or recommendation for setting like how you change epsilon I as iterations go forward?
I do. Okay, so this is going to be next slide. So the utility analysis. So here I was just saying, okay, essentially the privacy guarantee. Then there's how does it impact the optimization error, and this is where you can see some trade-offs appearing.
How each user define the sensitivity of SI?
How do you choose this?
Yeah.
So we assume each user has some epsilon I, some desired privacy parameter. Whether this is easy for a user in practical application to set, is another story. But assume each user says, okay, the value of epsilon I'm willing to accept is this epsilon I. Then essentially, this is the scale here that I'm assuming they use. This is just some parameter that depends on the loss function, this L0, which you can easily compute, and MI is the size of the local data set. So basically, they need to decide on the overall type of...
How did you understand that you should add this noise with this scale?
Oh, this comes from sensitivity analysis of the updates. Yeah, sorry if it was your question. So when I look at this update, okay, from theta I of t to theta I of t plus 1, this is how I update, and so I can look at this and see how sensitive that is to a single data point in the data set of the user I. And this gives me how much noise I should add. Yeah. All right, okay. I don't know how much time I have. Not so much. Okay, so, okay.
There were a lot of questions, right?
All right, I'll try to wrap up. But okay, here what we have is now, okay, we know how, okay, the privacy scales essentially with the parameters that I use. Now what I want to study is what is the impact, okay, on the utility. And this is the result that we got, okay? So this first term is the same as before, okay? This is the convergence rate from the non-private setting, okay, which goes to 0 as t goes to infinity. And now I have another term, which is an additive error, which is due to privacy, okay? And essentially it looks like this, okay? So this is for the most general case where the noise is allowed to be, the scale of the noise is allowed to be different across different iterations. If you assume users use constant scale, so they distribute their budget uniformly, this simplifies, okay, because essentially it's like a geometric series that converges, so you can simplify this term, okay. But essentially the idea here is that the amount of noise here shows up in there, and so you have some, for each iteration that you do, this is essentially an expectation, so it's like you are averaging all the noise scales that you use at a particular iteration and have a weight which depends on, okay, how far you are in the algorithm, okay. And so here, okay, I actually forgot to mention this, okay. One thing that I think makes this algorithm work well in practice is this assumption that we are in the collaborative setting. So I'm assuming that some users have no data or really few data, and so they add a lot of noise, okay. And clearly their updates are not giving any kind of interesting information from others. But because of this confidence that we have into the model, this noise is pretty much going to be ignored by the other users in the network. And on the other hand, agents that have more data, they're going to have less noise, and they're going to have more importance essentially in the network, and this is the information that's going to propagate, okay? So this is, in a sense, what makes the approach work. If you have all users and they have no data, okay, there's nothing really you can do. Here is really, okay, some users have more data and they can make the others sort of benefit from it, okay? And you can see it here also. So this scale of the noise for user I, it's also weighted by the CI. So essentially if this user has a really small confidence, even though this noise scale might be very big, it's actually not going to be weighted a lot in the error in the end, okay? And so what we got, I'm not making that clear here, but you can use this to try to see what scale makes sense in terms of noise. And it turns out to minimize this term, it's actually better to put less noise at the beginning, because this is where so essentially we have to trade off between two terms, right? Here is a term which goes to 0 when t goes to infinity. This is the optimization error. This is something that grows with t, okay? And so something that you can do is trade off between the two, and basically it's better to have less noise at the beginning because you make more progress here, and here you have sort of like a smaller weight also. So typically this tells you should scale the noise sort of inversely proportional to t. But what this result tells you is with respect to the global iteration counter, which is typically unknown, okay, in this fully decentralized setting. So, okay, how to implement this strategy in practice is sort of an open question. You can do approximately or in expectation, things like this.
So the dimension P is kind of implicit in L? Or doesn't appear anywhere?
Yeah, it's sort of implicit in L. But it depends also on the objective function, okay? So if you do things like logistic and things, actually dimension doesn't really show up. But yeah, okay, typically in the L max here. So there's results like this is the maximum and minimum Lipschitz constant coordinate, block coordinate was. There are some results connecting it to the global one, and okay, sometimes the dimension shows up between the two. But there are some nice cases also.
Time, and there's still the experimental evaluation, which I think is very interesting. So we could maybe restrain ourselves the question so that he can go through the experimental evaluation.
All right. This is going to be rather short, actually, the experimental evaluation, and so you're going to be probably disappointed. I sense there was some great expectation. Okay. So this is why also I call this illustrative experiments. Okay. So they're meant to illustrate the result. Maybe not to be so practically convincing. Okay, so here's the thing that I'm going to do. I'm going to do some collaborative linear classification. Okay, so I'm going to have 100 agents. They're each trying to do some linear classification task. Okay, and I use some classic loss like hinge loss. You could use logistic loss, whatever. They're all looking for a model in RP. Okay, just for simplicity, so we assume there's a target model, the true model of each user. Has only 2 coordinates that are active and the rest are zeros, but okay. This is more just to visualize the direction, okay? So you can think of these as trying to find, each one trying to find a different linear classifier in p-dimensional space. And we cheat a little bit here, so the network weights that I'm going to use, the similarity weights, I'm going to compute them directly from the target models. Okay, so this is where I'm cheating a little bit by using some sort of ideal version of those weights because I use the knowledge of the ground truth models to do this. Okay, so in practice you would need to estimate this based on the data. So it looks like this. Okay, so this is trying to show the angle essentially of the different linear classifiers, and what you can see is that it's all over the place. Okay, so if you, in particular, if you try to learn a single linear classifier for all users, this is going to have essentially 50% error. Okay, because there's too much variety. But still, okay, some users have separators that are not the same as other users, but are fairly close, and so sharing information there is going to help. Okay, so this is showing essentially the connections, okay, depending on the angle. This figure might be confusing, whatever. All right, and then each agent is going to receive a random number mi of samples. Essentially, I think in our experiment between 0 and 1 or something like that, 0 and 20. And the labels are given by the prediction of the ground truth models, plus some label noise to make things not too easy. And okay, and so this mi is, again, varies, okay? So it's going to be between 1 and 20, depending on the user. This is the kind of results that we got. So the x-axis is the dimension. The y-axis is the test accuracy, okay? So the model that I learned, when I apply it to some unseen test data, this gives me the accuracy. See that everybody goes downward with the dimension. This is because the number of training example overall in the network stays fixed, okay? So the higher the dimension, the more difficult it gets. This is the consensus model. So the one, okay, learning a single model for everybody, and so as expected, this is really bad, just because there's no good single model for this problem. This is just checking, okay, that we're in the case that we're interested in. The red curve is the solitary model, so learning on my own. And blue is model propagation. This was the simpler approach where I learn a model only on my own and then does this smoothing. And the green one is collaborative learning, so the one when I learn and propagate at the same time. Okay, and this is a non-private setting for now. So okay, we can see we can improve quite a lot on the upon the baseline of not talking to anyone. And that, as expected, also looking at the loss function as well as propagating at the same time is better than just pre-training and then propagating. And then this is the results we get for differential privacy, so the private variant. So here it is the same, okay, dimension versus test accuracy. Now we have like a bottom baseline and a top baseline. The bottom baseline is still the purely local models, which again you can see as perfectly private because it doesn't send any information to the outside. The top baseline is non-private approach. Okay, so our algorithm without adding any noise. Okay, and of course what you hope is that you are in between, that you can trade off between the two. Reveal a little bit of information, but getting some accuracy for it. Okay, and this is essentially what happens. So this is for different values of epsilon, from 1 to 0.1 essentially. And okay, so if epsilon is not too small, you manage to beat this perfectly private baseline of just looking at your own data. Okay. And so you can go a little bit deeper also and analyze what is the test accuracy depending on the size of your training data set initially. Okay. So this is for users that have between 10 and 20 points, 20 and 30, and so on. And this is accuracy of local models. This goes up typically. And then the private and the not private models. And what you can see exactly is nice is that all agents tend to benefit, which is good because it gives some incentive to for everyone to participate. And as we can expect also, the agents that had the smaller local data sets, they are the ones that benefit the most. Okay, so there's some kind of like a wealth inequality kind of correction here.
So this for a given fixed dimension. So what dimension?
This is for 100, if I remember correctly. Yeah. Okay, so this is the effect we see, and this is really because of this confidence. Okay, so for the ones who have more, what happens is that by setting this confidence higher to users that have more data, they influence positively the others, and at the same time they don't really move too far from their own stuff. Okay, so those in a way cannot really benefit that much. Okay, still the benefit, but okay. The ones with small data sets, they're more willing to change and get inspiration from others, and so this is sort of why they get a bigger boost.
And what's the accuracy of centralized learning?
So what do you mean by, centralized learning is?
All of them, we collect all of the data and then train the model on all of them.
Just a single model? Or?
Yes.
So single model would be this. Okay, it's really bad because on this problem, there's no single linear classifier that works well. So it's like 50%. Now, if you say, what if you centralize all the data and optimize the same cost function as I do? Then this is just, this, right? Because my decentralized algorithm optimizes exactly the same cost that I could optimize in a centralized setting. So, okay, all the algorithm I presented solved like a global optimization problem that I defined as being my target, that you can easily solve in the centralized setting, but not so much in the decentralized setting. But essentially, you converge to the same thing, right? So the decentralization is more like the constraints on the algorithm. Okay, yeah. All right. Okay, I'm going to try to conclude maybe. So maybe with some like future directions. So some things that I think would be interesting to investigate further around this type of work. Okay, so this came up by sort of the question of Borja, so how you can derive like statistical generalization bounds that make clear how you should choose those weights, okay, depending on how the distributions relate, maybe under some, let's say, clustering assumption on the user distributions and things like this. I think there's a lot of interesting things to consider. And along with this, some generic methods to estimate those weights. Okay, you can see theoretically what is the best weights, and then you can try to estimate them in practice. And then I think something that makes a lot of sense in this setting is to consider online learning. So essentially, instead of considering fixed data set, considering that data arrives sequentially, and in particular, you can use also the data that arrives sequentially to update the neighboring, essentially the network structure. Okay, as you see more data, you might realize, oh, this neighbor that you thought was good, maybe it's not so good now that I know more. And okay, so you could have sort of like a dynamic process that updates models and also the similarity neighborhoods. Okay. Like I said, this was more like toy experiments, so we were working on like real world experiments. We did already actually some work on recommendation. So movie lens type of data set. Each user sees only its rating vector for the movies that it's seen. And you do some like L2 regression essentially on this, and you can apply this algorithm. Works fairly well. Something that we're looking into is activity recognition, where, okay, so there's some data sets out there that are nice because you have some side information about users. So this is the setup where you have a smartphone in your pocket, and you do some stuff like climbing upstairs, walking, running, falling, whatever, and you're trying to predict this from the sensors. And okay, depending on the height, the weight, okay, the gender, and so on, this makes really personalized tasks, but obviously for similarly constituted users, you can share information. Okay, so it seems to fit quite well. But there's also like this multi-class stuff now that comes into the picture, and so you have to adapt a little bit the technique. Of course, it would be nice to extend to like non-convex cases. Okay, so here we're assuming like convexity in the loss, so that restricts a little bit the kind of things you can do. Obviously, you cannot do deep neural nets. Actually, you can do similar algorithm, but you don't have the guarantees. Okay, so it'd be nice to study a bit this. Okay, the centralized discovery of similar peers. This is more trying to relax this assumption that the network, communication network, and the similarity network are the same, which is sort of what I assumed here. Okay, you could make sure you distinguish between the two, and you have efficient ways of locating and sending messages to peers that might not be next to you in the communication network. And then something that I think is also really interesting is try to, okay, so here we still lose some accuracy because of differential privacy. There's, I think, a lot of opportunity here to use some, cryptographic tools to achieve better accuracy at the cost of more computation. So one simple example is obviously in all the algorithms that I presented, we do something like this, okay? So we do some weighted aggregation of the neighbors' models. And here what I do is I add the noise before I do the aggregation, whereas you could do the aggregation and add the noise on top of the aggregation, okay? And that would reduce a lot the amount of noise you need to add. So okay, there's a few places like this where probably you can benefit by sort of having sort of like a mixed approach. And that's it. Yeah, sorry for going a little bit over time.